Hello and welcome back to Calculus 3, section 11.4, the cross product. So this is the second lecture on multiplying vectors, and first big difference between dot product and the cross product is that the cross product works only in certain dimensions. It works in 3D, yay, right? And then it skips few dimensions, then it works in dimension 7 and so on. So cross product only works in certain dimensions. We will only be concerned with the cross product between two third-dimensional vectors. So now, we are starting again first with the way to compute the cross product, then I will go through definition and then whatever else we need to do. So, to compute the cross product, you have to compute the determinant of the 3 by 3 matrix. And if you haven't taken linear algebra, well, it's time to learn it now. I am going to start with vector u, and I'll just put ABC because it's shorter than writing u1, u2, u3, and the vector v as df. So this is our setup. Now, to compute the cross product u cross v, we are going to put in the first row ijk unit vectors. In a second row, we'll put ABC, which are the components of vector u, and the third row DEF, components of vector v. So it's always set up this way. First row, unit vectors. Second row is the first vector in a cross product, and then the third row is the second vector in a cross product. Now what we do is, and maybe it's better for you to observe to get the pattern and then just write out stuff. I start with I, and then that will delete that row and the column, and I only need to worry about the determinant of what's remaining, and that's a 2D determinant now. Now, the next part is the one where the grade usually goes down. You have to put negative j. The signs on these guys are plus, minus, plus. Bueno? All right. I said bueno. Oh, before that. Signs are plus, minus, plus. So, positive I, negative j. Once you put j down, delete that row and a column. We're dealing with the determinant ACDF. And finally, we have plus k you delete row and a column, and you have your A, B, D, E. So you compile the three two-dimensional determinants, and then you compute each one of those. The way these are computed is you multiply diagonals and you subtract. I like to put this symbol. Let me just draw this larger. A, B, C, D. Look, if I draw this symbol through, you see and you follow the motion. Observe that you have A times D, over here is flat, minus C times B. That's the way to visually memorize the way you compute the 2x2 determinant. So there is a intersection of these two lines is like multiplication. So you just go down the diagonal, multiply, and then over here is flat, that's a minus, and then multiply back and you exit this way. So if you apply that rule now, you have BF minus EC times I minus AF minus DC J, and then AE minus DB K. What is the result? The result is another 3D vector. So, cross product will produce another 3D vector. Dot product gives us a scalar. Cross product gives us a vector. So now, if you want to follow this pattern, let's do the cross product between 1, negative 2, and 4, crossed with 305. Set up and compute.
-10. That's 5 minus 12.
Do we all have vector -10, 7, 6? Good. I don't know what happened. Yeah, it's supposed to be a plus there. Probably the pen didn't catch. Maybe I went too quick. Right. Definition. Given two non-zero vectors, U and V, in R3, the cross product U cross V is given by magnitude of U cross V is equal to magnitude of U times V times sine angle theta, where theta is the angle between vectors U and V. I have this diagonal gives me 5, minus 12 is -7, and this negative is +7. All right. It's built in. I don't want to drop this one. All right. So two vectors are parallel if their cross product is 0. Because when the angle between two vectors is either 0, right, then they're parallel, or 180 degrees, they're still parallel. So no matter which way the vectors go, 0 degrees or 180 degrees, right, sine of 0 and sine of 180 is 0. So this theorem will state if the magnitude of U cross V is equal to 0, U is parallel to V. Put in the word then in between. This is going to be useful as well. Let's not forget that you can find angle between two vectors by using this very inefficient cross product, right? If you need to find the angle between two vectors, use dot product all the time. Now, if you like pain, You can also go with the inverse sign, because inverse sign of the magnitude of the cross product over there. Remember what you have to do. You have to do the cross product to find the third-dimensional vector. Then you have to do the magnitude of that third-dimensional vector. Then you have to do the magnitudes of these two vectors, and then do arc sign. I think that the dot product formula is much faster. So yes, you can use this to find angle between two vectors, but don't. All right. In interest of time and properties. Number one, anti-commutative property. Cross product is not commutative. It matters which vector is first, which vector is second. Therefore, you can't just put whatever you want. However, they are related into U cross V is the same as negative V cross U. Number two, AU cross BV is AB U cross V. This is called associative property. And there are two distributive properties. U cross V plus W, which is U cross V plus U cross W. And because we don't have commutative rule, we also have to do this backwards as a separate rule. So you get U cross W and V cross W. Clearly, the proofs for these are excruciatingly long, but possible. Yeah, don't worry about it. Cool stuff. I cross J is equal to what? Yes. So we have 1, 0, 0 cross with 0, 1, 0, which gives us IJK 0, 0, 1, 0, and that will give you K. And then you can play with the other ones. Cross product produces orthogonal vector no, that's the bad order. Hold on. Cross product produces vector orthogonal to the two input vectors. I think it's visible. We can make a vector field. That's chapter 14. The central problem of calculus 1 is the tangent line. Tangent line measures the instantaneous change. You can find the slope of the secant line using algebra. That's just the slope between 2 points on the straight line. Not a big deal. But the tangent line measures the instantaneous change at the point. So, when you are getting ticketed for a speed, you are getting ticketed for the speed you had at the moment when that speed was measured. That is the tangent line. That's the instantaneous velocity, which is the speed, and that's the one that is the derivative, actually. Now, as much as the tangent line is the most important concept of calculus 1, tangent plane serves the same purpose in calculus 3. In calculus 3, you have third-dimensional objects. Third-dimensional objects will have tangent planes, right? And this is the tangent plane. Now, this concept will play a crucial role in creating the equation calculating those tangent planes. So now, if you have two vectors which says find the orthogonal vector to the vectors 1, 2, 3 and negative 2, 4, 1. This is problem 36. So technically all you need to do is to compute. Let's compute the dot product. Surcharge. Yes. Surcharge. No. I counted the number of students. We have 26 in the classroom. We had 24, we can use the old classroom. The original one. We actually made fixed air conditioning yesterday. So, no, actually, it was just the old air. Because they has no windows. So, that air is about 20 years old there, so that's what's cool. But they fixed the air conditioning for some of the building yesterday, and if we had, less people come to class, then we could go to the classroom. So we might exercise this next week, take like you were a volunteer, not to come to class. Yeah, but the trick is that they are assigned to other summer classes, and they are also assigned to the camps that we run. Because the state is doing such a tremendous job in funding us. So instead of making you pay $1,000 for a class, you pay $700 for a class, and then we have the summer camps and so on to make those parents because they can't even take their kids to work. So we can, analyze that situation. Say, bring your kids here if you can, money, and then you got it. See, it all works out. Someone else is going to pay. And then actually, I think don't worry about it. Ignore it. And then you take that all right, so we have 1, 2, 3 cross -2, 4, 1. -2, 4. Yep. Oh. It's -2, 4, -1. Don't worry about it. We'll do it with 1. Problem 36 has a -1 over here. So this is not problem 36. It's close. All right. So what's the answer? So we have 2 minus 12. That's -10, right? Then we have 1. I don't know why I don't write it here. That's easier. All right, good. So that's 1. That's a 7. So that's -7. And then 4 plus 4 is 8. Good enough? All right. Fine. Don't put this on the exam. I do what I say, not what I do. I need to know that you know how to do this stuff, not your neighbor. Remember the policy on cheating? Day 1? It's in the syllabus, right? Application. So the first thing is we can calculate the area of the triangle and the area of the parallelogram using the cross product. So, two three-dimensional vectors, vector u and vector v, will create what we call a parallelogram. Parallelogram has two pairs of parallel sides. Rectangle is also a parallelogram, but it's a special kind of parallelogram because it has all angles to be 90 degrees. Parallelograms have two sets of parallel sides and two sets of equal angles. So now, area of this parallelogram is simply the magnitude of u cross v. If you cut this parallelogram in half, you will get a triangle which is defined by the two vectors u and v, and you can find the third vector by running the vector subtraction. That will define the triangle in space, and the area of the triangle, so this is area of parallelogram, area of the triangle would be 1/2 of the area of the parallelogram. So this is the first application to find area of the parallelogram and area of the triangle. And they're simply compute the cross product, take the magnitude, right, to find the magnitude of the resulting vector, and then if it's a triangle, cut it in half. The next concept is the concept of, again, go physics, or talk about torque. Torque is the force that works in a circle. If you are thinking about a wrench or a screwdriver, you actually have a right idea. And the way it works is that the magnitude of the torque is given as the cross product between the radius and the force. Now, these are vectors, right? To have the idea of what this is, think about the wrench. It has some kind of bolt in it. Now, you will apply force here, perpendicular to the handle. Clearly, if you push this way, nothing is going to happen. Now, that times the radius r will give you the force torque that works in a circle. End of story. The other concept that you can also quickly see this at work is the door. So I can do the experiment here because we have all of the lab equipment with us. This is a wall, looking bird's eye view from the top. Hinge door handle, and the rest of the wall. So if you are looking from, this is top view. What you are going to do is come in to the handle and push perpendicular to the door. The radius R is here, which creates the force around the hinge, and the door opens. Let's do the experiment. Now you also see that the amount of the torque, amount of the force, depends on how hard you push, which is force F, and the radius, which is how long the door is. So clearly the handle is going to be to the opposite side where the hinges are, and then you open it, right? Because you push perpendicular, and that's the force F times the radius that goes here. Now, you all know what happens when you push here as you go to the store, in and out of the stores, right? When it's not clearly marked. So you push here and nothing happens, right? Well, I'm infinitely strong, so, but if you try, you do nothing. So, the further away you are from the axis of rotation, radius is longer, more torque, and you push, and the door obviously opens. The same thing with the wrench. The longer the wrench, and then you have a breaker bar. What's a breaker bar? It's the extension, right? I don't know if you change your own brakes. I do. Sometimes it's really tough to get those bolts loose. What do? Breaker bar, right? There's no need for a muscle. It's need for higher IQ. It's easier. That's where it goes. The rest of the stuff, chapter 14. Now again, let's work on one of these applied problems to at least analyze it. Again, as soon as your formula in physics contains the force, your job is primarily to focus on figuring out how much force is actually applied. So, if you are tightening the bolt, and the bolt is, say, in the wrench, right, this is the bolt and the wrench, you pull straight down, that's the perpendicular force, and you are using maximum torque that you can possibly have, well, with the given force, because you are using the entire radius. The shorter the radius, harder it goes. Short screwdrivers with a skinny handle are bad, because on a screwdriver, the actual radius of the handle is the R that goes into your swing, right? Now, the problem is if you apply the force on the wrench at an angle, right? Sometimes you can't reach, you're fixing something in the engine or whatever, you can't reach to actually pull straight. You have to pull at the angle. Well, you better apply more force in that case, because when it's not perpendicular, what happens? Trig kicks in, right? And only the perpendicular component does the work. The rest is wasted. So, if I have a wrench, over here, and I apply the force at an angle, let's say of 40 degrees, well, only the perpendicular force is the one that, I'll call it force Y, is the one that does the work. So now, to calculate the torque, I will have the radius crossed with Fx. And this Fx is going to be the vector that is perpendicular to this. So that's going to be F. And now this is, again, adjacent. So it's cosine 40. You are not going to memorize this formula because in a different setting, that's going to be F sine 40 or whatever. You actually have to look at the diagram, which is the reason why in physics and engineering, diagrams and pictures are the most important thing in the entire problem. If you can't visualize it, you can't account for all the forces, and obviously the problem is going to be wrong. Another rule of engineering, draw big. As soon as I walk around the classroom and I see someone drawing the graph that is this big, you're not an engineer. And you might think you are, but you're not. Because you have to see what's happening, right? And a certain amount of OCD on a square paper. Yeah, I know. One, exactly. To have the graphs straight, to have divisions in a vertical and horizontal, the notebook is still $3, but you just have to get the right one, right? Not the college rule one. So that's that. That's the cross product. So for the cross product, we have to compute the determinant of the 3x3 matrix, which breaks into 3 2x2s. The definition is given with the sign of the angle. Hopefully you will not use this formula to compute angle between two vectors because dot product is much faster. If the cross product is 0, then the vectors are parallel. Properties, and the most important part is that the vectors create the two vectors in a plane, right? That's it. You only need two vectors to have the plane stable and defined. So the cross product of the two vectors, no matter which way they are oriented in space in 3D, that's the cross product, right? Will give you the orthogonal vector to the plane. That vector later on is going to be called the normal vector, and you'll be sick of it because that's what you're doing in chapter 11, the normal vector. So this is the rest of your chapter right here. Few examples: application, parallelogram, triangle, torque with a wrench and a door, and I'll see you tomorrow.